good day. So, in the last lecture we have seen some functionalities of the data link layer, namely framing, etc., and we had been talking off and on about that error control, that is error control means error detection, correction, etc. So, we will be talking about error detection, correction in this lecture. So, we will be talking about error control now. Now, data errors. When data is transmitted over a cable or a channel, there is always a chance that some of the bits will be changed or corrupted due to noise, signal distortion or attenuation, etc. Okay, so many things may happen. For example, suppose you have a wireless channel and suddenly there is a burst of noise. Okay, so what will happen is that some of the data will get garbled. Similarly, the data may have become very attenuated, maybe due to some loose contact somewhere or something, and then one that was sent was not received that way, or maybe it was received as a 0 or something. So, whenever you are sending some data or something, there is some communication going on, some transmission over some transmission line, you always have to assume that data may not go or I mean reach the other side in a perfect condition, and error control has to do with how to handle that. So, if errors do occur then some of the transmitted bit. Now, what is an error? Since we are talking about digital data, what will happen is that some of the bits by what do we mean by an error? So, 1 was transmitted, maybe it was changed to a 0, or a or from a 0 it was changed to a 1. Okay. So, this is the only kind of error that may occur, and actually if you knew where the position of that error is, we can actually correct it, because the correct one will be, if something we know is faulty, the correct one is just the reverse of it. So, if it is 0, then the correct one is 1, and if it is 1, then the correct one is 0. The whole trick is to find out whether any errors, any such change has occurred, and if such a change has occurred, where it has occurred, etc. So, this is or how to handle it. Sometimes I mean there may be a lot of noise and a lot of data may get corrupted in this fashion. So, we will see how or what we can do about this. Of course, this data error will also depend on your the kind of transmission medium we are using. So, that is always there. So, random errors change bits unpredictably. If each bit transmitted has a probability of being changed. These errors are often caused by thermal noise, because this thermal noise is something very general which is always present in any kind of this thing. There are higher thermal noise, or there may be low level of thermal noise, but this thermal noise is always present. So, these cause some random errors. Then there are some burst errors, change a number of bits in succession. They are often caused by faults in electrical equipment or by interference on some neighboring thing, etc. So, electrical interference is a very major cause of such burst errors. So, transmission errors, we take them as inevitable, resulting in the change of one or more bits in a transmitted frame. The rate of error may be high or low, but there will always be some error, that is what we assume. Let us just to see what it means, that if there is a finite probability of error for a particular bit, what it means, let us just have a look. So, some notations. Let PB be the probability of a single bit error, called bit error rate. So, the probability of a single bit error is the bit error rate, or BER as they are sometimes called. P1 is probability that a frame arrives with no bit errors, that means there is no error, and P2 is the probability that a frame arrives with one or more undetected bit errors. So, P1 is no error, P2 is that one or more error. P3 is a probability that a frame arrives with one or more detected bit errors, but no undetected bit errors. So, sometimes we can detect that which bit are in error, sometimes we cannot. Okay, we will come to this later. And let F be the number of bits in a frame. If no error detection scheme is used, suppose we are not detecting things specifically. So, P3 is 0, we cannot detect which bits are in error. So P1 will be equal to 1 minus Pb by to the power f. If you remember, Pb is a bit error rate. Since Pb is a bit error rate, probability of a single bit error, so P1 would be 1 minus Pb for one particular bit. If one particular bit, the probability of error is Pb, so so the probability that for that particular bit there is no error is 1 minus Pb, and we are assuming that these errors are sort of independent, which may not always be the case in case of burst errors, but for thermal noise at least we assume, let us say, that these errors, or whether the noise will introduce an error or some other error will creep in, let us say they are independent. So if there are f bits in a frame, so the probability that there is a frame arrives with no error is 1 minus Pb to the power f, and P2 that it arrives with one or more error is 1 minus P1 naturally. So clearly longer frame and higher Pb leads to lower P1. Let us try to look at some numbers. So this is an illustrative example. A defined specification for ISDN connections. You remember ISDN means integrated service data network, which is the digital service given through the telephone lines. So that is the ISDN. So ISDN connections is that bit error rate on a 64 kbps channel should be less than 10 to the power minus 6 on at least 90% of observed 1 minute intervals. Now suppose, so that looks quite a low rate of error, that means 1 in 10 to the power, that means only in a million bits only 1 bit may come in error. Suppose we want that at most one frame with an undetected bit error should occur per day on a continuously used 64 kbps channel with a frame length of 1000 bits. All right. So we want not more than one frame should come with undetected bit error. All right, and so we are using this for a whole day on the 64 kbps channel, and the length of the frame is 1000 bits. So number of frames transmitted per day is equal to 64 kilobits per second divided by 1000, that is the number of frames per second, into 16 to 16 to 24, so per second becomes per day, is approximately 5.5 into 10 to the power 6. Desired frame error rate P2 is equal to 1 by, so if one of them is this thing, so desired frame error rate, we say that not more than 1 out of all these frames can be in fault. So 1 by 5.5 into 10 to the power 6 is 0.18 into 10 to the power minus 6. But if you assume Pb to be 10 to the power minus 6, then P1 is equal to, so 10 to the power minus 6, so we have 6 nines after the decimal point, to the power 1000 for each frame. So P1 is 0.999. There, so if P1 is 0.999, P2 is 1 minus 0.999, which is P2 is approximately 10 to the power minus 3, which is about 3 orders of magnitude too large to meet our requirements. That means it is 1000 times more. So although 1 bit in a million looked fairly good error rate, but we find that at the end of the day we have maybe 1000 frames which are in error. Well, it does not work out that way. By multiplying with 1000 you will get so many frames in error, but the point is that whatever probability we required for a faulty frame, we got a much higher probability than we were prepared. We were prepared for, say, one faulty data frame per day, but that is not the case at all. So this necessitates the use of error detection. That means we have to do something to bring down this error rate. The point is, the other point is that sometimes one will not have control over the environment or the transmission line directly. It is quite difficult in the sense that I mean, if you are having a wireless transmission, now whether some noise will suddenly come from some other source, okay, maybe somebody starting a car will also give out some kind of electrical noise, and somebody starting a machine somewhere will give some kind of electrical noise, some mixer or grinder running in the house may give some kind of error. So, all kinds of sources are there, you do not have any control over it. So, the point is that whatever the errors that is coming, you have to do something at your end to get better error rates. So, we want to detect such errors and if possible to correct them. So, this is what we were going to discuss now, error detection. One general principle of getting greater reliability or less error etc., as I said, is always redundancy. That means you put in some kind of redundancy in the system in order to get better reliability. We have seen this when we were talking about reliability of optical networks etc. But in this case, the redundancy comes in the form of extra bits that we introduce into the data, which means that I mean whatever data that is being sent, we also send in some extra bits specifically for the purpose of error detection and correction. So, EDC are the error detection and correction bits which are actually redundant, that means they are not an original part of the data, they are extra bits which have been introduced. Suppose D equal to data protected by error checking may include header fields. So, the data which you are protecting, this may or may not include, it depends on the protocol etc. It may be just be on the payload, or it may be on the payload and the header all together, we may like to detect the error. Error detection of course is never 100% reliable, okay. But protocol may miss some errors, but usually we can bring down the level of errors to a very low figure. The larger EDC fields yields better detection. Naturally, if you put larger redundancy, you have better error detection and correction. So, you have the datagram coming. So, D data bits, we add some extra bits EDC, then we send it to a bit error prone link which arrives at D dashed and EDC dashed. Okay. Now, D may be the same as in D dash, no error etc. EDC itself may have been corrupted, both may have been corrupted etc. But anyway, we run some algorithm or some method for finding out whether or not these are all right, and if we think they are all right, we say yes, otherwise we say that an error has been detected. Well, even if we say it, the errors may be such that even if we say that everything is okay, maybe everything is not okay, all right. In that case, we will say that the error has gone undetected. Now, for this error detection and correction, one concept which is used is the so called Hamming distance between two bit patterns. Okay, we will and then there are Hamming codes also. We will not go into the details of Hamming codes here, but let me just tell you this, what is a Hamming distance. Suppose you have two code words, okay, like it has been shown here. So, this one code word is 10101110 and the other one is 01001101. Okay, these code words. By Hamming distance, what we mean is that in how many bit positions the two code words are different. Okay. So, in order to find that, we simply XOR the two. So, if we XOR this, we get this, if you can go through it, 0 1 is 1, 1 0 is 1 and so on. So, you get 1 1 1 0 0 0 1 1. So, we say now we count the number of ones in this XOR, which is 5. So, we say that their Hamming distance is 5. Please note that if the two corresponding bits are different in the two code words 0 and 1, 1 and 0, then we get a 1 in the in this XOR. If they are the same like 1 1 or 0 0, we get 0. So, these are H Hamming distance is the number of positions where the two code words differ. Okay. If you have a set of code words, say between this and this Hamming distance is 4, between this and this the Hamming distance is 3, between this and this also the Hamming distance is 3. Let us see, this differs in one position, two positions, these are the same, third position, this is again the same. So, this is differs in 3 positions. Similarly, these other H3, H equal to 3, H equal to 3 for other pairs, all right. So, in this set as a whole, the minimum Hamming distance between two code words is actually 3. So, H of the code word is actually 3. We take the minimum of all these H values, and this comes out to be 3. So, we say that this for this set of code words the Hamming distance is 3. Now, if the Hamming distance is 3, we have an interesting situation, which is that if now let us say these code words are what we are sending to the other side. Now, if at a particular if there is a single error, that means what? That a single bit has flipped from 1, it has become 0. So, what has happened is that this code word will move to another code word. So, this will appear as another code word in the receiving end, and the one which is received and the one which was sent, the Hamming distance between the two will be only 1, because only one bit has flipped. So, only one position, what was 0 here has become a 1 there, or maybe what was 1 here has become a 0 there. So, only in one position it has changed. So, assuming that there is a single bit error, the Hamming distance between the transmitted and the received code word will be 1. Now, if the system is known that this is the set of code words which is being used on both the sides, first of all you will immediately know that this particular, and suppose for this set of code words H is equal to 3 was there. That means say this is the set of keywords that I showed you, say that those are the only code words which are being sent. So, the Hamming distance was 3. So, the for whichever you I mean, so this new transmuted or new changed code that was received is not going to be a valid code, because this is only at a Hamming distance of 1 from the transmitted code. So, this is not going to be a member of the set. So, immediately you will detect that there has been some error, and not only that, if you assume that there can only be, I mean it is most likely that we have got only one error, then it is the one which is at a Hamming distance of 1 from this transmitted code will be at least at a Hamming distance of 2 or more from other code words, whereas it is at a Hamming distance of 1 from the code word which was already sent. And if you know this, and if you assume that there can be only one error, then you know that that is the code word. So, you can not only detect that there has been an error, you can also correct the error by going to the nearest code word from which the Hamming distance is the minimum, namely the one which was transmitted. Okay. So, this is a general principle. So, we will see practically how this is done. So, therefore, there is a coding scheme for which goes as Hamming code. So, we will not discuss that, but there are other schemes, but all of them use this idea of a Hamming code, that Hamming distance. Now, the simplest error detection scheme is a parity check. It appends a parity bit to the end of a block of data. So, what is a parity bit? So, this is an extra bit which is sort of added to some data. There are two kinds of parity, odd parity and even parity. Odd number of bit errors can be detected. Why odd number of bit errors can be detected, etc. I will explain that. If an even number of bits are inverted due to error, an undetected error occurs. The technique is not foolproof, as noise impulses are often long enough to destroy more than one bit, particularly at high data rates. But let us first of all see what is a parity bit. So, suppose 10110111, this is the this was the original bit pattern. In even parity, what we do is that we make the number of we add a bit which is 0 or 1 depending on whether the number of ones in the original pattern is even or odd. If it is even parity, we want to make the number of ones even. So, the number of ones were originally even over here. So, in 10, 110, 111, we have 6 ones, 1, 2, 3, 4, 5, 6. So, we already have an even number of ones here. So, in the added parity bit, we just give it a value 0. Whereas in the other one, there is 1 1, 5 zeros and then 1, we have 3 1s. So this was odd. So the added parity bit was also made 1, so that overall the number of 1s in the in this data plus parity bit taken together is always even. Okay, that is the point, that the number of 1s is always even in even parity if everything is fine, and the number of 1s is always odd. Similarly, the number of 1s is always odd in odd parity. Now, if you just think about it a bit, if you are using even parity, then all the valid code words have even number of 1s in them. So, what is the number of positions, what is the minimum number of positions in which they have to differ, two different code words have to differ? Well, the minimum number is 2. That means the Hamming distance of this set of code words will be minimum 2, and if the Hamming distance is 2, and if there is a single error, what is going to come is that we are going to get a code word in the receiving end which has got an odd number of 1s. And if it has got an odd number of 1s, we immediately know that this could not be a valid code word. So we know that there has been some error, although we cannot say that which where that error is or what the original intended transmitted one is, because if you think of two code words which are at a distance of 2, and the transmitted one, because of its and both of them, let us say, have had even parity, that is even number of 1. So their Hamming distance was minimum was 2. Let us take the worst case, the minimum is 2, and then the transmitted one of these, suppose this code word was this thing where one of the bits flipped. So we get something in the middle. So we get something in the middle which is at a Hamming distance of 1 from two valid code words. So we know that this whatever has been transmitted is invalid, in the sense that this is not a valid code word. So an error has occurred, but I do not know whether something from here came here or the original transmitted code was here and it came here, because we do not know where the error has occurred. So in this particular case, we can merely detect an error, we cannot correct it at the receiving end. All right. So this is a case of parity. This is a very simple kind of scheme. So once again, if you go back to the earlier slide, I mentioned that odd number of bit errors can be detected. Now, as I said, that a single error, if there is a single bit error, it will be detected, because now we have got an odd number of 1s. Well, if there are an odd number of errors, that means whether if there are 1 error or 3 errors or 5 errors in that bit stream, then again we will get an odd number of 1s on the receiving end. So we will know that this is, we can detect that there has been an error. We do not know whether 1 error or 3 errors or 5 errors, but in any case we can detect it. But if there are only 2 errors, then it will again become an even number of 1s on the other side, which may be a valid code word. So we will not know whether there has been any error or not. So if there are an even number of errors, and this parity check will not it will go undetected by this single parity bit error checking. Okay. And I mean, just generating the parity bit, etc., that is very easy. You just run them through some XORs. So and invert it if you want it odd parity, or if you want an even parity, you can get it. This is very simple. Now, parity testing. The receiving device can work out if a bit has been corrupted in a character by counting the number of 1s in the character and parity bit. If even parity bit is being used, but there are an odd number of 1s, then an error must have occurred. Similarly, if odd parity is being used, but there are an even number of 1s, then an error must have occurred. One drawback with parity testing is that if 2 errors occur in the same character, they will not be detected. This is because if there were an even number of 1s originally, if 2 bits are changed, then there will still be an even number of 1s, because either 2 1s will become 0, so the even number of 1s remain even, or 2 zeros will become 1, so even number of zeros will remain even, or 1 1 has become 0 and 1 0 has become 1, so the number of 1s do not change, so they still remain even, so it remains undetected. There is a sort of some improvement over this to make it more efficient. So, this is an extension of parity bit which is called block parity testing. This is how it works. Okay. So, suppose we have a long string of ones and zeros, 1 0 1 1 etc., whatever it is going on. So, what we do is that we break them up into blocks of bits, let us say 8. So, first 8 bits we take as the first pattern, then the next 8 bits as the next pattern, and so on. Okay. So, what we do is that for each group of 8 bits, a parity can be added, in this case let us say even parity. So, if you have, so my first 8 bits were 1 0 1 0 1 1 1 0. So, we for even parity there are 5 ones here, so I have to add a 1. There are 3 ones here, I have to add a 1. There are 4 ones here, so I add a 0. So, this way for each block of 8 bits we add a parity bit. Okay. Then for every n blocks the parity is calculated as a new character, in this case 8 into 8. So, this is how it goes. What we do is that if you look at this as some kind of a matrix, so we calculate a parity on this side, we calculate a parity along the column also. So, 1 1 1 1 1, so 5 ones, so we make it a 1 over here for this this parity. So, then for every n blocks the parity is calculated as a new character that I have mentioned. So, I have got parity on this side, I have got some parity bits on this side, all right. So, I so for this block of say 64 characters, I have got say 8 plus 8 16 plus 1 17 parity bits I have used. Now, I mean if an error occurs, what is going to happen is if there is a single error which has occurred, what is going to happen is that wherever it may have occurred, in that row the parity test will fail. Similarly, in the column also the parity test will fail, and since one column and one row intersects exactly at one cell, we know that that is the bit which has become corrupted. So, now if an error occurs, we will know which character and which column it has occurred in. Not only have we detected the error, but we can also correct a single bit error by simply changing it. So, since we know that this is the bit which is in error, I can simply flip it, and now at the receiving end itself, without any referring back to the transmitter, and we know that and we have got the correct one. So, we can not only detect errors, we can also correct single errors in block parity testing. So, this is another just better diagram for this. We have got this system. So, this is using say odd parity. I mean there is no reason to use the same kind of parity in both the cases. You can use odd parity for the transverse parity bits for these, and you can use even parity for these and calculate this. So, if there is some error, we can compute it. By the way, if there are more than one error, then you may get into some kind of trouble, because you will not know that which bit is in error, because if there are 2 rows and 2 columns which show parity error, then you may sort of you will not know which row and which column will match together to give that particular bit which has been corrupted. So, we can not only have error detecting codes, we have some error correcting codes also. Of course, compared to error detection, error correcting codes require more number of bits, because we want to correct it. So, we require more number of bits. So, that is a bit of a problem. So, in error correcting codes, rather than just detecting an error, sometimes it is useful to be able to correct an error as well. For example, CDs use error correcting codes to ensure high quality sound reproduction, even if the CD is slightly damaged. All right. So, we are talking about some music CD or something. So, even if a few bits are in error, still it will use error correcting code to handle that. We have already seen that we can correct a single error in a block parity check. There are other techniques that can correct more number of errors. So, what happens is that your one scheme is could be errors detection. So, suppose some alphabet A was sent. So, this was a valid code word. There was a noisy channel. So, some error got introduced. So, 101101 became 100101. That means the third one from the left has become a 0. So, this is an invalid code word. We know that the original one had let us say was using odd parity kind of thing. So, even number odd number of ones were there, but in the sorry, even parity. So, even number of ones were there, but I got an odd number of ones. So, I have detected. I do not know where the error is. So, what we do is that we request for retransmission. That could be one sort of approach. But if I can sort of correct a single error on the other side, then I do not need to ask for retransmission. Naturally, overall my efficiency may improve, but of course for error correction I have to send more bits. So, that is one area where I am sort of losing something also. So, it all depends on how you do your engineering and how you come to your particular point of say optimal amount of error correction. So, another way for checking for errors was to use a checksum. Okay. This checksum is also used in other fields. So, this has been borrowed not just from communication, from other fields for accounting etc. Also sometimes checksum is used. What you do is that this is just used for this sum is just for control purpose. So, you sum some arbitrary in some arbitrary order, you sum it and then you with all the data you also check with the sum. For example, another way of checking the errors with checksum, this is a number calculated from the data and sent along with the data. If any errors occur during transmission, then checksum for the received data will differ from the transmitted checksum. Of course, the data may arrive all right, but the checksum may become sort of faulty, but even in that case the checksum and the data they will not sort of match. So, checksum, but this can only detect errors, it will not be possible to correct it. Simple checksum can be calculated by adding all the data together. For example, if the data is 121, 17, 29 and 47, then the checksum if you add all this will be 214. We could transmit 121, 17, 29, 47, 214. So, we know that the last number is the checksum. So, which should be the sum of all the numbers which have been sent. The checksum is usually restricted to a certain number of bits, typically 16 bits. If the checksum is longer than this, then only the lower 16 bits will be transmitted. But checksum is not very efficient and not very widely used. One scheme which is widely used is the so called cyclic redundancy code. What is a cyclic redundancy code? A cyclic redundancy code is a more sophisticated type of checksum. If a CRC is used, it is extremely unlikely that any errors will go undetected. A lot of different types of errors are caught by the CRC. Although the technique may sound a little complicated, in practice calculating a CRC is easy and can be implemented in hardware using linear shift register. So, which is a very simple kind of circuit. So, through that we can sort of compute it very easily and quite fast. So, that is why CRC is preferred in many data link protocols. So, what is CRC? Let us just look at the details of it. Essentially, the data is regarded as being one very long binary number. After all, what you are sending is a string of ones and zeros. So, you can take a few of them and just look at it as a binary number, although the original intention of the user or the, I mean if you are adding the header also, then it got even more mixed up. I mean it was not to be interpreted as a number, but for CRC purpose we interpret it as a binary number anyway. So, to this we add some placeholder digits and then at the end, and it is divided by a generator polynomial using modulo 2 division. So, modulo 2 division there is no borrow. So, basically you do the same kind of division, only thing is that if they match and then you get a 0, if they do not match you get a 1 as you are doing a division. We will see this. The remainder at the end of this division is the CRC. So, let us just look at this. So, given a k bit block of bits, the transmitter generates an n bit sequence known as a frame check sequence, so that the resulting frame consisting of k plus n bits is exactly divisible by some predetermined number. The receiver divides the incoming frame by that number, and if there is no remainder, assumes there was no error. So, this is the scheme. You sort of look at it as a number, then find this CRC, add it to the n. So, what will happen is that you will get a longer number. This longer number is supposed to be divisible by that polynomial which the receiver side knows. So, the receiver side will do its own division, and if the division is okay, then it will assume that there is no error. If it is not okay, then obviously there is some error. So, we have D data bits and suppose R CRC bits. So, how are the CRC bits computed? D into 2 to the power R XOR R. So, this is done by some division. So, as we will see how it is done. So, this is the formula D into 2 to the power R by G. This is the generator polynomial. Why it is a polynomial, that we will see. Actually, the bit pattern is represented as a polynomial. Ultimately, this so called polynomial will be a binary number like this. Suppose the G is 1001 and what you are trying to send is 101011. So, this is what we are trying to send, and this is the generator polynomial. What we are going to do is that we are going to add some extra bits. So, this is by D into 2 to the power R, by multiplying by 2 to the power R means so adding so many zeros at the end. So, in this case say R equal to 3. So, we have added 3 zeros to the end, and I do a division as is done. So, 1001. Only thing is that this I mean where we usually subtract, we do a modulo 2 kind of operation. So, 1 1 gives 0, 1 0 gives 1. So, we got a 101. So, we got a 0 and so on. So, this way the division goes on till we sort of exhaust this, and this we get as the remainder 0 1 1. And what will happen is that, and the point is that if you add this 0 1 1 over here, so instead of sending 101 0 1 1, what we do is that we add 101 okay. So, this is there seems to be some problem over here. Anyway, so if you add it, what will happen is that this will become exactly divisible modulo R. That modulo 2 division will come out exactly. So, the CRC process can be very easily implemented in hardware using LFSR, linear feedback shift register. The LFSR divides a message polynomial by a suitably chosen divisor polynomial. So, why polynomial? I will look at some of the polynomials. The remainder constitutes the FCS, which is added to the data bits. Commonly used divisor polynomials are CRC 16 is x to the power 16 plus x to the power 15 plus x to the power 2 plus 1. So, actually it is a 16-bit binary number. As I said that G, this is the G. So, this is the so called generator polynomial. So, G will have 1 in the 16th position, 1 in the 15th position, 1 in the second position, and 1 in the first that is 0th position. So, which means that there is going to be 4 ones in this G, and all the rest are going to be 0. By the way, usually for some purpose this usually this is kept as odd, you will find. So, actually how this generator polynomial, so we are not going into that how this particular polynomial, why was this particular polynomial chosen rather than some other polynomial, but these have been seen that they cover a lot of different types of errors. Okay. Previously, if you remember that in our parity bit we were just sort of getting a even number, that is odd number of errors. If there are an odd number of errors, then we can detect it. Here we can detect a lot of different cases of error. So, it is extremely unlikely that if the CRC is all right, that there has been some error. So, there are different protocols and different systems use different generator polynomial. So, CRC CCITT is x to the power 16 plus x to the power 12 plus x to the power 5 plus 1 and so on. This is CRC 32 and this is CRC 8. So, CRC 8 means this is an 8 bit this thing. So, the 8th position, 2nd position, 1st position and 0th position, 8th, 2nd, 1st and 0th position. So, these are all ones, rest are zeros. So, for this is used in ATM. CRC 10, this may also be used, CRC 12. So, these are different CRCs. Actually, not all polynomials will give you the same kind of error coverage. So, that is known, and people have found out some of the polynomial, people have found some properties which are good properties to have in a generator polynomial, and then people have found out some good polynomials which will cover a lot of errors. So, HDLC uses some kind of error, say CSMSCT, FDDI, ATM, they use CRC 32 like this and so on. So, I mean this is just for showing you, you need not remember any of this. Now, we come to the slightly higher level data link protocols, in the sense that we are still talking about errors and error control, but the point is that we have been talking about this parity and CRC etc., that is error control at a lower level, so to say, where at a lower level a small amount of error we can possibly handle it using such error detection or error correction kind of scheme. But what might happen is that because of a very burst of noise or something, it may garble the data so badly that it is entirely unrecognizable on the other side, even if you have a data error correction scheme, because all error correction and error detection schemes, none of them are 100% 100% infallible. So, there is still possible that there will be some undetected errors, and then there will be the data may become so bad that there is no question of any error detection or correction. So, we require some higher level schemes also, in addition to whatever we have talked about, this parity, CRC etc. So, these higher data link protocols, well, once again they could be of different types. For example, unrestricted simplex protocol, this does not do much, as we will see. Stop and wait protocol, stop and wait with stop and wait ARQ for a noisy channel. That means ARQ stands for acknowledgement request. That means an acknowledgement is expected. 1 bit sliding window protocol, which is similar to this stop and wait, sliding window with go back and ARQ, sliding window with selective reject ARQ and so on. First, unrestricted simplex protocol, well, it simply sends, it does not do any kind of error control. So, this is the simplest situation. So, we have a sender, fetch a packet from a network layer, construct a frame, send the frame to the physical layer. So, sender is just going on sending without any kind of bothering about what is happening on the receiver end. Receiver, usually if things are all right, wait for an event, receive a frame from physical layer, pass the packet to the network layer. So, if there are some faulty things which have gone in, it is possible, maybe it is the responsibility of higher layer systems to take care of that. This does not bother, or maybe the higher layer application does not bother if a few bits are bad, say in the case of a voice channel. Okay. Now, sorry. When data is sent as a sequence of frames, two types of errors can occur. One is that lost frame has been lost entirely, the frame fails to arrive at the receiver. This may be due to a noise burst destroying the frame beyond recognition, or it may have a recognizable frame arrives at the receiver, but some bits are in error. So, a frame may be damaged or a frame may be entirely lost. see, say sender and the receiver, sender is sending a number of frames, frame 1, 2 to frame n. So, frame 1 is going first. So, the point is that some of the frame in between may get lost altogether. So, this is a very bad thing to happen, but this may happen. We have to make the worst case assumptions. Now, error control is concerned with ensuring that all frames are eventually delivered, possibly in order to a destination. So, how? 3 items are required: acknowledgement, timer and sequence number. So, acknowledgement, what do we do with acknowledgement? Well, typically reliable delivery is achieved using the acknowledgements with retransmission paradigm, whereby the receiver returns a special acknowledgement frame to the sender, indicating the correct receipt of a frame. That means, the receiver, after receiving a frame, will send an acknowledgement. Okay. In some system, the receiver also returns a negative acknowledgement for incorrectly received frame. So, what this is a hint to the sender, so that it can retransmit a frame right away without waiting for a timer to expire. We will come to this timer to expire. So, the point is that there is a two-way communication. Sender is sending the frames, the receiver is sending the acknowledgements. Okay. If it gets a damaged frame, then it will send a negative acknowledgement. Of course, if it does not get any frame, then it will not know whether anything was sent at all. So, in that case, it may not send any acknowledgement or negative acknowledgement, anything at all. All right. So, the situation is something like this. Suppose 0 was sent by the sender, so it arrived. So, the receiver sent an acknowledgement 0. Then a 1 was sent. Suppose I am just taking this bit by bit just to make it simpler. Suppose 1 was sent. It came with some error. We do not know what kind of error. So, so the frame number 0 was acknowledged. Frame number 1 was received, but it was damaged. So, negative acknowledgement was sent. That means, frame number 1 was not rightly received. So, frame number 1 is going to be retransmitted by the sender. This is the argument. The other thing is that the other thing we require is a timer. Timer means that one problem that simple acknowledgement, negative acknowledgement schemes fail to address is recovering from a frame that is lost. A frame is totally lost. So, the receiver will neither send an acknowledgement nor a negative acknowledgement. So, and as a result fails to solicit an acknowledgement or a negative acknowledgement. What happens if an acknowledgement or negative acknowledgement becomes lost? Retransmission timers are used to resend frames that do not produce an acknowledgement. When sending a frame, schedule a timer to expire at some time after the acknowledgement should have been returned. If the timer goes off, retransmit the frame. So, this is the scheme. You see, a frame which was sent was lost. So, the receiver of course did not know anything. What happens is that as soon as the frame was sent, at the same time a clock was started in the sender's end. So, it assumes that knowing that the system, that this is the transmission time and this is the time it might require for the receiver to process it and then send an acknowledgement, and the acknowledgement will take some time to reach the sender, etc. So, all that is taken into account with some extra amount of time thrown in, and that is set in the timer. So, if the timer goes out, that means if there is a timeout, now the receiver sender knows that the frame must have been lost, otherwise an acknowledgement would have come. So, he sends the frame again. All right. The other thing that might happen is that suppose the frame was sent, 0th frame was sent, it was received all right, and then an acknowledgement was sent and the acknowledgement was lost. Of course, he would not know whether the frame reached at all or the acknowledgement was lost. So, after a timeout, he will send this frame again. So, this is a case where the frame has been duplicated. Of course, the point is that the receiver, depending on what kind of protocol you are using, the receiver may or may not understand that this frame is actually a duplicate of this. Maybe two such exactly similar frames were supposed to come one after the other, because it is after all coming from some application which is absolutely unknown to the data link layer. So, a frame may get duplicated, but then there are some protocols which take care of that, where the receiving side will know that this is actually a duplicated frame. Okay, we will come to that protocol later on. And the third technique that we use is the so called sequence number. So, retransmission introduces the possibility of duplicate frames, as we have just seen. To suppress duplicates, add sequence numbers to each frame, so that a receiver can distinguish between new frames and old copies. Okay. So, this is a so that if the frames are numbered sequentially, like say 0, 1, 2, etc., as I was sort of showing, and if the receiver gets two frames which have the same number 0, so it knows that the acknowledgement must have got lost or something like that happened. Anyway, the sender sent the same frame twice, so he will discard just one of them. So, collectively the mechanism stated are referred to as automatic repeat request. Okay. ARQ. Objective is to turn an unreliable data link into a reliable one. Three versions of ARQ have been standardized: stop and wait ARQ, go back and ARQ, and selective reject ARQ. Then we have the stop and wait ARQ, which is based on the stop and wait flow control technique. The source station transmits a single frame and then waits for an acknowledgement to arrive. No other data frames can be sent until the destination station's reply arrives at the source station. So, it waits for the acknowledgement. And the point is that if the acknowledgement does not come, it will resend after an automatic repeat request. So, it will automatically repeat the frame. So, this is the scheme. We have the sender which fetches a packet, construct a frame, send the frame to physical layer, wait for an event. So, if it gets an acknowledgement, then it is fine, then it is going to go and send a second frame. If it does not get an acknowledgement, it will send the same frame again. So, until it either gets an acknowledgement or the timer runs out, the frame which was already sent, that has to be stored locally in some buffer or something in the in whichever system is handling this data link control. And the receiver side also, it waits for an event, receive a frame from the physical layer, pass a packet to the network layer, send an acknowledgement to the physical layer. So, this is the stop and wait protocol. This is a very simple protocol. Unfortunately, this is not very efficient, as we will see later on, and so we will continue our discussion on this error control, and then we will move on to flow control, etc., in the next lecture. So, this is a simple kind of protocol, but this has got efficiency problem, in the sense that this is not very efficient. Okay. So, we will continue this discussion in the next lecture. Thank you.